Hi, welcome back to our session. Last time we have seen the curve sketching couple problems, last video. Then this one we still continue, So we have seen three different type of questions already. Then this one, we see another one. Then we move on to the next section, section. Well, 2x to the 5/3 minus 5x to the 4/3. This one gives us a not the polynomial but the radical function. We have simply the power is a rational that, well, x to the 5/3, that is cube root of x to the 5th power, That's what the 5/3 or 4/3, that's cube root of x to the 4th power. That's what they are, So they are simply the radical function, but we get the odd radical, so it's not even radical, It's odd radical that we have the domain. We can take all real number as the domain. The domain of odd radical function is all real number, For negative taking in, that's negative. For positive taking in, that's positive. That's what we have. First, always to find the domain first over R, That's our always the first step to do, to find the domain. The next is to find our intercepts. Y-intercept is a little easier. X-intercept, well, we need to let f of x, that is 2x to the 5/3 minus 5x to the 4/3 equal to 0. Then we need to factor out the greatest common factor, which we have constant 2 and 5, nothing to be factored out, but x to the 5/3, x to the 4/3, we're able to factor out x to the 4/3. We get 2. Then 5/3 minus 4/3, that's 1/3. And 4/3 cancel, taken out, that's what it is. So we get x to the 4/3 equal to 0. 2x to the 1/3 equal to 5. That x to any power equal to 0, x has to be 0. And x to the 1/3 equals to 5/2. That x, what we do is the 1/3 power is over there, so how we solve for x is cube it. I take it to the 3rd power, that the function will be cancelled, X equals 5/2 to the 3rd, that's 1/25 over 8. So that is our x-intercept. Well, we get 0, 0, and 125 over 8, 0. Which 128 over 8 is 16, So this is a little smaller than 16, 125 over 8. Then for y-intercept, f of 0, of course, is 2 times 0 to the 5/3 minus 5 times 0 to the 4/3, which both of them are zeros, that we get is 0. So the 0, 0 origin is both x-intercept and y-intercept, and also x-intercept itself is 125/80, right, the point. Right, we can find out by the calculator 125 divided by 8, that's about 15.625. Right, so about 15.6. Right, so a little bit more closer to 16. Right, but that's our intercept. And clearly, right, we have a radical functions that we do not have any asymptotes. We don't have any asymptotes because we have a radical function, right? Asymptotes only able to from the rational function, or it may be from the something we see before, right? When limit approach to infinity or negative infinity. But we can see this one, the polynomial basically, right? Or radical is another type. It's not that much polynomial, but especially it will not end, right? It doesn't have any bounds. So we don't have any intercepts, right? Like what we see last time, 1 plus e to the negative x. Since exponential function has bound and it's a rational function, so it maybe have bounds, right? Have the asymptotes. But these things will not have bounds. Has similar behavior, in other words, as polynomial, but they are not polynomial, right? Something more need to be considered. So for the increase or decrease interval, we need to find out, well, what is our f prime of x. Right, this just apply the power rule, 2 times 5/3 times x to the 2/3. 5 times 4/3 times x to the 1/3. Right, that's 10/3 x to the 2/3 minus 20/3 x to the 1/3. Right, this one also defines everywhere. So we don't have the part to be undefined since we have positive power of x always. Right? So to find the critical number, we just find f prime of x equal to 0. That we are able to factor, right? 10/3 x to the 1/3 out. Get x to the 1/3 minus 2. Right, to solve for that, we get x to the 1/3 may be equal to 0, or x to the 1/3 minus 2, that could equal to 0. That x equal to 0 or x equal to 8. Right, they are our critical numbers. You could put a point as the value as we showed the last time, or you could say critical numbers are x equals 0, x equals 8. Besides, you could put the values, right? Don't have to put the point. But always the point we need to evaluate it out, so it's also fine to leave as point. And maybe seal the result for f prime x on the side, since I'm gonna using it. after we factor, could be the root 1. Right, so that is our result, and for the derivative. Right, then we just check the increasing decreasing interval and to find out what can we say about the points. Right, but before we do that, we need to find out what is f of 0. Which is the thing we found already in the previous step, right? That's already 0. And f of 8. Maybe we could use the radical expression, that will be a little easier. Cube root of 8 to the 5th power, cube root of 8 to the 4th power. That's 2 to the 5th is 32, 2 to the 4th is 16, 5 times 16, that's 80, right? 2 times 32 is 64, we get negative 16. So we have 2 points, right? 0, 0, and 8, negative 16. Then we have the table. From negative infinity to 0, from 0 to 8, and from 8 to infinity. 3 values we're able to take. In 3 intervals we cut the domain into, right, since there are 2 critical numbers. Then the test value and the shape of f prime of x, or the sign, and the shape of f of x. Well, we have the first derivative is that, so maybe we could take the number to be perfect cube in that interval. Negative 1 is perfect cube, 1 is a perfect cube, and after 8, the next one is 27. Right? So, cube root of 1, a negative 1 is negative 1. That we have 10 over 3 times a negative 1 times a negative 1 minus 2. That will yield to negative times negative is positive. Right, for the 1 similarly, cube root of 1 is 1. Then 10/3 times 1 times 1 minus 2, which is a positive times negative, give a result to be negative. And 27, cube root of 27 is 3, right? That we get 3 times 3 minus 2, which both of them are positive, yields the final result to be positive. That we get increase, decrease, and increase for those intervals. A positive of f prime yields or let the f of x to be increased function, and negative of the derivative makes the original function to be negative, to be decreased. Right, so we have negative infinity to 0, 0 to 8, and 8 to infinity. That we get our increase, decrease, and increase for the interval. And we get the 0 is a relative maximum, and our 8 is relative minimum. 8 negative 16 is our net relative minimum, and the 0, 0 is our relative maximum. Right, from the idea of the first derivative, right, for the first derivative test actually, right, to see the monotonicity and to see the relative extrema. Right, that's this part. Then after we see the increasing, decreasing of the function, we still cannot get a smooth curve, right? The smooth curve I'm able to get from the view of the concavity as well together, right? To see if a function is smoothly continuous or sharply continuous from the view of the concavity as well, that together. That's our first derivative, right? I have it on the side. Then f double prime, that is 10 over 3 times 2/3 x to the negative 1/3 minus 20 over 3 times 1/3 times x to the negative 2/3. Right? Apply the power rule and the power minus 1. 2/3, 2 over 3 minus 1, that is negative 1 over 3. 1 over 3 minus 1, that is negative 2 over 3. Right, so we get 20 over 9 x to the negative 1/3 could be flipped down. 20 over 9 x to the negative 2/3. It could be a little larger written. Right, that's our second derivative. And what we can do is multiply the first fraction by x to the 1/3. That we get x to the 2/3 times 9 on the denominator, which we're able to subtract it on the numerator. Right, that we get 9 x to the 2/3, 20 x to the 1/3 minus 20, and factor out the Right, so that is our second derivative. After we simplify everything, 20 x to the 1/3 minus 1 over 9 x to the 2/3. Right, then the next part is to see, well, what are the possible point of inflection. That's our f double prime. Double prime of x, that is 20 x to the 1/3 minus 1 over 9 x to the 2/3. The possible point of inflection is occurred at f double prime equal to 0 or f double prime x is undefined. Right. That's two parts. Occur equal to 0. That is where the numerator equal to 0. We know 20 cannot be 0. That only x to the 1/3 minus 1 could equal to 0. And we take the third power to both sides, that x equal to the 1. Right? And for the double prime is undefined, that's the denominator equal to 0. Which we take the inverse of the whatever it is, right, to the 3/2 power, then on both sides we get x equal to 0. So possibly at x equals to 0, that is totally fine, right? The 0 is part of our domain, so possibly it is the possible point of inflection. Alright, so possible point of inflection at x equal to 0, x equal to 1. Well, we only see it's possible because we don't know actually what the point of inflection gonna be, right? But it's possibly change the concavity at those points, right? If they change, then yes. If not via the point, then or going through the point, then they are not the point of inflection. Right, so the table we built for the interval that's negative infinity to 0, the middle 0 to 1, and then 1 to infinity. Test value, the sign of f double prime. And then the and the shape of f of x. Alright, test value for, well, we're looking for a perfect cubic since we take the cubic root over there. We see that, well, f double prime of x, that is 20x to the 1/3 minus 1, 9x to the 2/3. Which the denominator is always positive since that's even power, right? 2 over 3, which whatever the cubic root afterwards, we take in the squares, right? So it has to be positive. Then the top we have positive 20 multiply a unknown, x to the 1/3 minus 1. Right? So if x to the 1/3 minus 1 is negative, then the whole thing is negative. If it's positive, then the whole thing is positive. Right, so we kind of do not care about the denominator at all. Right? So for test value, we still need to take a perfect cubic, that is -1 can take. In the between 1 and 0, we can take a cubic of 1/2. Right, not wrong at all. Right, cubic of 1/2, that's 1 over 8, and we take cube root of 1/2 to the 3rd, that is just 1/2, right, which is still in between. And after 1, we can take the value of 8. Right, so -1, we take a 3rd radical of it, that's still -1. So for -1, that is a positive number multiplied by -1 minus 1, that will be negative. For 1/2 to the 3rd, that we get a positive number, whatever they are, multiplied by 1/2 minus 1, which is also negative. And for positive 8, right, the test value, that's positive number multiplied by cubic root of 8, that is 2 minus 1, whatever it is, that is positive number. So we get concave down, and concave up. We get concave down, and concave up for 3 intervals, which look like, well, we are going through the 0, right? That's nothing being changed in the view of concavity, right? They both still concave down. So possibly 0 is a point of inflection, but actually it didn't change the concavity. So this one, the point 0, 0 is not the point of inflection. One more thing we need to do is, well, to find f of 1. Since it looks like the 1 is the change of concavity part, 1 is changed. Right, so f of 1, that's 2 times 1 to the 5/3, 5, 1 to the 4/3, right, substituting in, that's 2 times 1 minus 5 times 1, negative 3. Right, so the point 1, 3, 1, negative 3, negative infinity to 0, 0 to 1, 1 to infinity. We have concave down, concave up. Right, 0 is not second differentiable, right? It doesn't have make the second derivative undefined at the 0. So anyhow, right, the 0 actually could be omitted, but we just show it all together, which is also fine. And the 0, 0 is not the point of inflection, but 1, negative 3 is the point of inflection. Is our point of inflection. Right, so intercepts, asymptote thing, increasing, decreasing interval together with critical number and the relative extrema. Second derivative, possible point of inflection intervals to show the concavity, then to see actually which point is our point of inflection. Our point of inflection which needs to change the concavity going through that point. Right? The 0 is not. Then finally, wrap up everything. Right, to wrap up the intervals, we have the critical 0, 8, inflection 0, 1. So we have seen the cutting interval from negative infinity to 0, from 0 to 1, from 1 to 8, and finally 8 to infinity. 4 pieces. We get the shape from the first derivative, shape from the second derivative, finally the summary of how the f of x looks like. Right. We get, before 0 is increasing, from 0 to 8 we get a decrease function, and after 8 we have the function increase again. Right, that's our first table tells us. And our second table tells us, well, before 0, actually before 1, everything is concave down. And after 1, we'll have concave up piece. Right, so the function is increase and concave down, the left piece of the concavity part, increase and concave down before 0. And from 0 to 1, that's decrease and concave down. And from 1 to 8 is decrease and concave up. Finally, it's increase and concave up. Right, 4 partitions. So you get 4 pieces from negative infinity to 0, 0 to 1, 1 to 8, and 8 to infinity. We get increase and concave down, decrease and concave down, decrease and concave up, finally increase and concave up. Right, that's our summary of what they looks like. Right, based on the table and what else we have are the intercepts, the relative extrema, and the point of inflection. Possibly asymptotes, this one doesn't, then use the 8 of them to graph our curve. we have the 0, 0. Five, 10, 15, 20, and the 1 maybe is here. -1, 10, 15, 20. -16 is what we need. The detail, we don't have to show that much. Since we have something we need, we should have. Right, that 8 is over here. Right, if you draw your own picture, if you have a graphing paper, of course it will be much better, right? Then if you don't have, then of course it's also fine, just mark the point nicely. Well, you get the 0, 0 is our x and y intercepts, as well as the relative maximum. And the other point is 8 to -16. Right, the point 8, -16 is our relative minimum. What else? The point of inflection is at 1, 3, 1, -3. I label clearly that 1, -3 is the point of inflection, right, this point. And the another x-intercept we have is 125/8, 0 is our x-intercept. Right, which if you want to, right, you could make the line to refer to that point if you want. Right, that's these lines. Then the curve is based on the intervals, right? We have all the points are set, the special points are set already, the origin, the 1, -3, our point of inflection, our relative minimum, and another intercept. Right, so before 1, we have this decrease and the concave down. I mean increase and concave down. Right, increase and concave down all the way to the origin. Then after the origin, we have concave downwards, but it's decrease. Right. That is a little bit showing the curve of decrease and the concave down. Then after that, is change the concavity and make it concave up. Right, from 1 to 8 is decrease and concave up. And after we have all the way is increase, increase, and concave up. I just follow the shape of what we have seen in the last table. And we mark all the special points. Possibly if we have asymptotes, we should mark them, but this question doesn't have any. Right? So that is what we have. Right, so that picture is how we deal with the graphing, right? How we will deal with the graph. So we're taking that long time to deal with the curve sketching, which because it's that curve sketching is wrapping up everything such that the knowledge from our pre-calculus and which are what's the domain, or finally we forgot the range, right? The curve, what's that? Kind of. Right, and the range of this curve we take all real number. Right, I just forgot that. But anyhow, range was just one little last thing that if you see carefully, if the question asks you to find range, you could state that. If not, then it doesn't matter. Which curves, which wrap everything up together, right? Of the domain, range, the x-intercept, y-intercepts, x-intercepts, y-intercept, and the vertical, horizontal, slant asymptote, right? That's from pre-calculus, and also what we've seen that about the first derivative, about how to find the critical numbers, use the first derivative test, which in the usage of increase-decrease interval to see what we have, the critical numbers are the relative extrema or no, right? That is the one part. And second part is second derivative, and to find possible point of inflection, then use the concavity to check if the possible place are actually our point of inflection or no. Then together, right, in the section of first derivative for increase-decrease, and then the section of second derivative of concavity could be wrapped together, right? Could be build a table together to show the shape of the original function to see what it is, and use all the points, asymptotes to draw the final curve. Right? That's the curve sketching, which is overall everything together, right, of what we have learned.